Hello and welcome back to Refactoring Bitcoin. Today we will dive a little bit deeper into the topic of type erasure, as I promised last time. But we stay mostly in Compiler Explorer today. Consider the following. We have a function, we have a class, we call it foo, and that class has a public function print, say public and print. And we simply output, simply write hello from foo. Line break. And in the example, let's say we have a client, call it client 1. And what the client does, it can create an object of type foo, initialize it foo, and then what they can do is print the object by calling the print function object.print. And in our main function, we invoke the client just for testing this, okay? We compile it and we see the expected output, hello from foo. Now consider this. We add another class, call it bar, and this other class has the same function. It also has a function print, print, and here we simply output hello from bar. We type hello from bar. Very similar. So those two classes now, we can say that those two classes have the same interface. Not in the sense that they are derived from the same base class, but in the sense that they give the same promises. So in the client, we can actually replace foo with bar, and we compile the program, and we see that the output changes. It's now hello from bar. But no change was actually necessary in the source code. The functions provided from foo are the same ones that are also provided from bar. This is what we say when they have the same interface. Okay, but client 1 actually is not interested in bar. They want to use foo. And they're actually very pedantic. Let's say foo is implemented internally. It has used, it uses an integer. We don't care about the value of the integer. We just imagine that it is there. We initialize it with some value 21. And foo, the client 1 is actually very picky that the size of the type foo is not bigger than the size of an integer, right? This is the zero overhead principle that some people are very picky about in C++. So client 1 makes an assertion that size of foo is actually identical to the size of int. And we compile, and this still works, okay? But now consider there's a second client. Let's say there's client 2, and client 2 has the requirement they want to use both both foo and bar. Let's say they want to use them polymorphically, like put elements of foo and bar into a vector and then print them all. This could look like this. They create a vector, but we don't know what type do we want to put in there here. But we know they want to use them like this. So they want to iterate over all the elements. Like this vec, and then they want to invoke here, let's say they on the elem they want to call print. Okay, but the question is, what do we put here in the angle brackets? Let's comment that out for a minute. The classical approach to abstraction, object-oriented programming, would be to introduce an abstract base class. Let's say we create a class printable, and this will be abstract. So we add a virtual function print, and we make this pure virtual. So we do virtual print pure virtual with equals 0. And now we want to override to inherit foo and bar from printable. And we can add override here. Override. Okay. The problem is now that client A says, over my dead body, will you make that change? Because this adds overhead to my type that I want to use. And I'm not interested in the polymorphic behavior, so I'm not willing to pay this, pay the price of this overhead. Okay. Client 2 would be willing to pay the overhead because they have the requirement for polymorphic behavior, but client A does not. Client 1 does not. Okay, so this is not an approach that we can use to create this abstraction. So we revert those changes and also remove the override keyword here again. But you remember from last video, we used type erasure to return a callable object from a function, from a lambda expression. So we copy in the source code from previous video. Let me take this here and I copy it and I put it right before client 2. So this is our function int that we have, and I just want to rename a few parts here. Instead of the function, we call this a printable, which also in the constructor printable. The argument is not a closure, we just call it arg. Okay, we forward it to the model, and of course, instead of the calling operator, we want to have our print function. So the function will be called print. We remove the arguments, and the function, the virtual function that we call here, will be called do print. It doesn't take an argument, and this will be the name of our virtual function. Sorry, just do print, but it returns void and does not take an argument. And in our model, this is not called a closure. We just call this object, and the argument will be called arg. Let's just make this shorter, just like this. So the object will be initialized from the argument. And here we have a do print function. It returns void, does not take arguments, and we call the print function on our object. Dot print. So we don't need this return. And now that seems to be fine, right? Now we made all the replacements. And now we can actually use this in our client too. We create here a vector of printable objects. And the interesting observation that we can make here is that this printable now also has the same interface as the types foo and bar. They both have this print function, and also our printable has the same interface. So here's the semicolon missing. Now in client 2, we can add elements to the vector, like in place back. We can add an object of type bar. and we can create, we push back objects of foo, and we see that compiles. And the output that we get is nothing, of course. We need to invoke client2 here, client2. And if you recompile now, then we see the output of the client1 function and the client2 function. So client1 produces hello from foo, and client2 produces hello from bar, and then again hello from foo. What we see here, this is exactly matching the elements that we have put into the vector. Good. But type erasure is not limited to member functions. It's interesting. It can also be used with free functions. So imagine that this print function here in the type foo is implemented as a public function, as a free function, as a free non-member function of class foo. We say we pass foo here as an argument. And remember I said that non-member functions are also part of the class interface. So this print function here, previously it was a member function of foo. Now we say it's a non-member function of foo. We do the same with bar. We also extract the function here and put it outside the class. And of course we want to parse bar as an argument. Then in our client, we have to change the syntax. Instead of calling the member function here with the dot syntax, we have to pass the object to the function. But this client1 now compiles, and we have to make the same change here in the in our type erasure implementation. We want to pass the object to the print function. Okay, this still does not compile because it thinks it's the print function here above. We also need to make this print function a non-member function of the printable type. The problem here is that since the print function accesses a private member, we have to make this a friend function. So we have to extract the function, put it outside the printable implementation, and here we have to put a forward declaration. So we say friend print, and it would take printable as the argument. Okay, like this. But interestingly, many people don't know this. You can actually implement friend functions inline at the place of the declaration. So instead of putting the function here down below, this print function, we can actually put it back and implement it inline. So we put this here, and we invoke p dot point the do print function on the pointer that we access on the printable object that we pass as an argument to the print function. And finally, we have to change the syntax here. Pass lm to the print function. And if we compile now, we get the same output that we had before. We now type erase. Previously, we type erased a member function. Now we type erase a non-member function. And as you can imagine, this can be mixed and matched. So the space here in our type erasure pattern, currently we only have a single virtual function, but there could be any number of virtual functions. You could type erase a mix of friend functions, a mix of member functions and non-member functions, as you will. We can use this pattern to expose an interface of a type without exposing its actual type. I think that was enough theory. Now we actually want to see how we can make use of that in production. So we want to go back to our implementation of the Bitcoin kernel. Here, we see here, this was the outputs function that we had. We had this, this view transformation expression. And we like the implementation of that, but we see here that the type that this expression produces is this ref view nested inside a transform view. And what we actually want to expose to the client is just the fact that it is a view over our, what type is it actually? Our It's a view of transaction outputs, and we want to hide the implementation of this CTX out type and the vector and the ref view and the transform view. So type erasure is exactly the pattern that we want to use here, but we will do that in the next video. So I hope this was not too complicated, this video. It will get simpler in the future again, I promise. And it will also get less dry, more interesting, because we're working with actual code and not so theoretics. Yeah. That was it for today. I hope you liked the video. Please subscribe to the channel, follow my refactoring, and also tell friends about the channel. And yeah, help me increase my reach. Thank you very much, and goodbye.